Bismillah ar-Rahman ar-Rahim. Last time we discussed the min-terms and max terms, and we stopped at the conversion between the two canonical forms, how to convert from sum of min-terms to product of max terms and vice versa, okay? And also we discussed how to get if complement. If you are given if in one of the forms, how to get if complement in the two other forms, okay? So please go and study that, study this by solving exam questions, okay? Okay, so today we are going to discuss the operations on canonical forms, okay? So what are the operations? We mean logic operations or binary or Boolean algebraic operations. We can add two sum of min terms, and then the result is going to be the intersection of the indices, okay? Let me show you what I mean by this, okay? It is an example. So we have functions of A and B, okay? This is A and this is B, and this is F and this is G, okay? And this is F ANDed with G. So F ANDed with G is going to be just the ANDing of these two columns, right? So it's going to be 0 here and 1 here and 0 here and 0 here, right? So let me test your knowledge about the what we covered last time. What is f of A and B in sum of min terms form? What are the min terms of f? Guys, wake up. Come on. Yeah, we got an answer in the chat. Okay. 1 and 2. Excellent. Excellent. That's a correct answer. Can you answer the second one, please? For G as well, the G as a sum of min terms.
0, 1, 3.
Yeah, excellent. 0, 1, 0, what? 1 and 3, right? So this one is just 1 and 2 because you have at row number 1 of the truth table, we have a 1, and row number 2 at the truth table, we have a 2. So it's 1 and 2. And this one is 0, 1, 3 because we have ones in row number 0, 1, and 3, okay? Now, if you would like to AND them, you basically take the intersection of the two functions, okay? So the intersection of 1 and 2 and 0, 1, and 3 is what?
1.
Just one.
1. This is the only term that occurs in all of them, okay? And to verify this, just do the AND and check what is the from the truth table, what is the sum of min terms here? It's only 1 here. See? So only if a min term belongs to this function and this function, it will appear in the ANDing of the two functions if we are expressing them in sum of min terms. Okay, so this is why the first one is take the intersection of the indices. Okay, now by the same concept, or by the same argument, we can show that ORing of two sum of min terms results in union of the indices. Okay, you can show this by, or you can illustrate this using truth table as well. Okay, but we are not going to. I'm going to leave this for you. Okay, to do that. As well as ANDing of two product of max terms, it's going to be the union, and ORing of two product of max terms is going to be the intersection. Okay, now let's take an example. We have F and G. Okay, F is given in sum of min terms and G is given in product of max terms. Okay, we would like to find F ANDed with G in sum of min terms form. Okay, so the way to do this is to AND the two functions here like this, but we haven't learned how to AND sum of min terms with product of max terms. So we have to change one of them to the other in order to solve the question and use these rules here. Okay, so since we want the answer to be in sum of min terms, we will change this to sum of min terms. Or in fact, no, I'm sorry. We want the answer in product of max terms in this example. Okay, so we change this to a product of max terms. So this is going to be a product of max terms 2, 4, 6, and 7 multiplied by product of max terms 1, 2, 3, 4. Okay? Why 2, 4, 6, 7? Anyone can tell me why? Did we change this to from this to this?
Because we have two variables and 8 different results.
Excellent. So these represent what? Indices that are what? Are not showing up in this list, right?
Yes.
Yeah. So now we have two a product of max terms ANDed together. So what do? The union, right? We take the union of the two and we get this. Okay. The union of this and this. All right. If the question was in sum of min terms, then you change this to a sum of min term and then do the intersection of the two. Okay. All right. So here is another example. So we would like to find if ORed with G, if this is the case here. Okay. So the answer is in sum of min terms. So we change both to sum of min terms. Okay. And then ORing here, it means that we are going to take the union of the two lists. And the answer is the union of the two lists. What about if ORed with G in product of max terms? It's going to be the product of the terms what? If ORed with G is going to be equal to product of big M of what? Anything that doesn't show up in here, right? Because this is F or G in sum of min terms. Okay. So anything that doesn't show up here, any index that doesn't show up here will be in here. So this is going to be 2, comma 4. That's it. Right? Okay. Any question? Okay, so let's move on to what we call standard forms. Now, the standard forms are the more general forms than canonical forms. So canonical forms are a special case of standard forms, okay? For standard forms, we define two concepts. Like in canonical form, we defined the min terms and max terms. Here we define a product and a sum. Okay, a product, oops. A product term is an ANDing of one or more letters, okay? So these are examples of product term, A, B, A, B, C, A complement, B, C complement. So we don't worry, we don't care about whether the literals are all showing up or not. Since it's, if it is a product term, then it's a product term, that's it, okay? So in this case, a min term is a special case of a product term because we, in addition to being a product term for the min term, we require it to contain all the literals in the system, okay, whether complemented or uncomplemented. We can define also a sum term by the same way, to be the ORing of one or more literals. Okay, these are examples of sum terms, and the max term is a special case of sum term because, again, a max term is a sum term such that all the literals occur. Okay, but a sum term in general is just an ORing of some literals. Okay, so we can express any Boolean function as sum of or product of sums. Okay, form. These two forms are called the standard forms. Okay, sum of product, or abbreviated as SOP, and product of sums, POS. Okay, these two forms, SOP and POS, are called the standard forms. Okay, so we would like now to indicate from these Boolean expression which one of them is SOP and which one of them is POS and which one of them is not in standard form. So the first one, who can tell us whether it's a sum of product or a product of sum?
Sum of product.
Sum of product. Why? Because we have two products, okay, and they are summed here. Okay, excellent. What about the sum of products, not sum of minterms? Okay. What about the second one?
Product of sums.
Product of sums. Okay, because why? Because we have a sum here which is ANDed with another sum here. Okay, what about the third one?
Sum of
Sums of
product.
products.
Sum of product, right?
Yes.
Sum of product. Okay, so sum of product, it means that you have product terms here, right? This is a product term, that's correct. What about this? This is the whole thing is a product term, correct? But what about inside? It's a sum.
Product of sums.
Okay? Sum here. So this is a sum, a product of sums, and the whole thing is a sum of product. So this is not in standard form. Not in standard form. Okay, so this is not in POS or SOP. Okay, what about the one, the next one?
Sum
A
of
or
products.
the CD?
Sum of product.
Sum of product. Excellent. Why?
We can assume that there is a one.
We
beside
have
the A.
products here, A and CD. These are products and they are summed. Remember that the definition of the product is ending of one or more letters, okay? Although it doesn't
Okay.
mean anything to AND one variable because the AND is at least a binary operator. But if you have one literal, it's considered a product term or a sum term, depending whether the form is a sum of product or a product of sum. Okay. What about this one here? The last one. It's a
Sum of product.
sum of product.
Product
Isn't
of
it
sum.
product?
Product.
Yeah, product of sums. Yeah, because you have here a product, you have here a sum, and here you have a sum as well. So sum can be one or more letters, or one or more letters. Okay. Okay. So what about this example here? This is it in standard? First of all, is it in standard form or not?
No.
Yes.
Okay, somebody said no. Why? It's actually in standard form. In standard form. Okay, so which one of the standard form? This is the question to you.
This is a product of sums.
Product of sums. Why? Because it's a product and each one of these is sums. Okay. What if I add a 0 here. Does it change the result?
No.
It doesn't, right? It doesn't change the result, right? So it's also a sum of product, okay? But it's so this one here is really depends on your interpretation. So this is not this is you can interpret it as you wish, but it's similar to this one here, A or B. Okay, A or B, you can think of it as a sum of product or a product of sums as well, right? So it's exactly the same. So these are two fringe cases, okay, that you can think of, okay? But the normal cases are these. Okay, so moving on, we have what we call the two-level implementations as well, in which both the standard and canonical forms result in two-level implementations. When we say implementation, we mean logic circuits, okay? So both the standard and canonical forms result in two-level logic circuits. So for sum of products and sum of minterms, we have one level of AND gates, okay, followed by one big OR gate, okay? So the total is two levels, okay? So here is an example. So if we have F that is equal to the sum of minterms 0 and 3, okay? I know that 0 and 3 is equal to A complement B complement, ORed with AB, right? Okay, using algebraic representation of minterms, okay? All right, so this is in logic circuit. It is basically an AND, an array of AND gates, okay, generating the products, followed by one single OR gate, okay? So this is level 1 and this is level 2. So this is two levels implementation, okay? And for obvious reasons, this is also referred to as and or implementation, okay? So whether we say and or implementation or sum of minterms or sum of products, okay, they all refer to the same thing, okay? All right, what about this example here, which is a product of sums, okay? So the product of sums also is a two-level implementation, okay, in which we have an array of OR gates or generating the sums, okay, and then one big AND gate, okay, at the end to generate the product of sums, okay. And this is level 1 and this is level 2, okay. So both product of sums or product of max terms generate a two-level implementation, as well as sum of products and product of and sum of minterms generate a two-level implementation, okay. So for the same obvious reasons, okay, this implementation here is also referred to as OR and implementation, okay, OR and implementation. Now, if your circuit or logic circuit contains more than two levels, then you immediately know that your circuit is not in standard form, okay? So, for example, here, this circuit here has level 1 and level 2 and level 3, okay? So we know from just by looking at the circuit, we know that this is not in standard form. And to verify this, you can derive the logic expression of this, and you'll see that it is not in standard form, okay? Because this is the whole thing. If you look at the big picture, it is a sum of product, but this one is a product of sums, okay? So it's not in standard forms. Any question? Okay, let's move on. So now we talk about what we call the propagation delay. Okay, propagation delay. So far in the course, we have assumed that all the gates have zero delay, okay, in which whenever the input changes, the output changes instantaneously, okay? However, in practice, this is not the case, okay? In practice, there is some delay in which the output is influenced by the input, okay? Here is an example. So we have an inverter here, okay, in which the input signal is X and the output signal is Z. And this is the ideal, what we call waveform, okay, in which we have the X as input, okay, changing like this with respect to time, okay, horizontal axis is time. So it starts with a 0 and goes to a 1 and then goes to a 0 again and 1 and so on and so forth, okay? The output, ideally, the output will follow the input signal without any delay. So the output here is going to be, since the input here is 0, the output is going to be 1 here, and it will remain a 1 until the input changes from 0 to 1, in which the output will change instantaneously from 1 to 0, okay? And so on and so forth. So the bottom line point here is that the output doesn't change, doesn't have any delay with respect to the input, okay? This is the ideal case. However, in real life, okay, or practice, this signal here is shifted to the right for some milliseconds or let's say maybe nanoseconds or picoseconds in new technologies, okay? So it's shifted to the right by some time, very small amount of time, especially for the inverter, which is a high-speed circuit, okay? So we expect in practice to see some sort of delay. So if the input changes from 0 to 1, we expect the output to not change instantly, but have some delay and then responds to the change in the input, okay? So this delay here is referred to as the gate propagation delay, okay? The gate propagation delay, okay? And it's denoted by the letter tau here, okay? These plots, okay, are referred to as timing diagrams, and also they are referred to as waveforms as well. You can generate plots for and or a whole circuit if you want to, okay? But right now we are discussing the propagation delay. So let's talk further about the procedure for finding the longest propagation delay in logic circuits, okay? I think the best way to explain this procedure is by giving an example, okay, and then coming back to the procedure to summarize what we just did, okay? So let's consider this example for the sake of calculation of the delay from input to output, okay? We are given this circuit here, and I'm numbering the gates here, gate number 1, gate number 2, 3, and 4, and 5 here, okay? And we are given the information here, we are given the propagation delay of every gate here, okay? And we would like to know the longest propagation delay from any of the inputs to the output here, okay? So is it from A to F, and how long it is? Is it from B to F, and how long it is? Is it from one of other inputs to F, and how long it is? Okay, so we are given individual propagation delay of every gate here, as in this table. So here, for example, a 2-input AND or OR gate, okay? So an AND or OR gate with 2 inputs, okay, has a delay of 2 nanoseconds. So here, for example, if the input changes, if one of the input changes, you will observe the effect on the output after 2 nanoseconds here. Okay, similarly here. Okay, so if one of the inputs changes, you'll observe the effect after 2 nanoseconds after this change occurs here. Okay, so our objective now is to find the delay of the output delay of every gate, starting from the input, not starting from the input of the gate itself, but starting from the primary inputs. Okay, so for example, from here to here, for example. Okay, what is the delay? All right, so we need to calculate the delay according to the worst case in this case. Okay, so yeah, so I have drawn the circuit below here, and at the beginning we have to assume that the delays at the input signals are available from time 0. Okay, they are available without any delay. So I'm going to reflect this fact by marking every input, okay, by 0 here. Every input has 0 delay, right? I'm not saying 0 as logic 0. No, it's 0 nanoseconds. Okay. All right. Now this 0 is for all of this wire here. So the delay in at this input of the OR gate, of the big OR gate here, okay, is how long? It's 0 as well. Okay. Yeah, you see that? Okay. Now we are ready to calculate the delay across this AND gate. We know that the delay across this AND gate, okay, starting from here to here, is nothing but the given in the table. Okay? And that is what? 2 nanoseconds. 2. So since this wire is the same, this one here is the same as this and this, so this 2 will propagate here and here as well. Okay? All right? Is this clear? All right. Now, we want to find the delay of this gate here, this inverter here, okay? The delay across this inverter from this inverter, okay? From the output to one of the inputs, not from, so what is, according to the table above, okay, according to this table, the delay from here to here is just 1 nanosecond, okay? But we would like to find the delay from one of the inputs to here, okay? So in this case, we know the delay up to this point, which is 2, right? So what do? I add this delay to the delay of this gate, right? And this results in how many nanoseconds at the output?
3.
3, excellent. Yeah. So we know that the delay at the other input of the OR gate is 3 nanoseconds. Okay. What about this OR gate now? The delay at the output, okay, starting from the inputs is, if you see the table here, it is 2, okay? 2 input OR gate has a delay of 2, propagation delay of 2 nanoseconds. So the delay from here to here is 2 nanoseconds, okay? So this is 2, okay? And also this is 2 as well, okay? Because they are the same wire. Now for this AND gate, we know that the delay from here, from these 2 inputs to here is, as given in the table, it's 2 nanoseconds. However, I want the delay from here, from one of the inputs to here, or from here to here, whichever results in the maximum delay, okay? So we know that the delay up to this point and this point is 2, so they are equal, so we take one of them, okay? So we take one of them, which is 2, and add that to the propagation delay of the AND gate, and the result will be what? The delay
4.
at excellent 4. Okay, so this is going to be 4 as well. So we have here a wire that has 0 delay, and another wire that has delay of 3 nanoseconds, and a third wire that has 4 nanoseconds. So to account for the worst case, we have to wait all the way for the longest delay, right? Which is coming from this wire, okay? So the delay across this OR gate is going to be the delay of a 3-input OR gate, again, an OR gate with 3 inputs, okay? Which is given here to be 5 nanoseconds plus the delay in the maximum input, maximum delay in the input, okay? Which is input number 3 here. So 4 plus 5 is equal to 9 nanoseconds, okay? Now, this is the delay from the inputs to the output, okay? And this is the worst case delay, okay? Or the longest delay, we call it. And to find the path that is responsible for this delay, the path that is responsible for this delay is called the critical path, okay? And we can traverse it back from the output, okay? We start from the output all the way to the input, and in each at each gate we select the input that has the highest delay, output delay, okay? So we start from here, and then we go to input number 3 here, and here we have a choice, okay? We either go here, and here we have another choice here, or here, or we can go here as well. Go here or here. So one critical path, one of the critical paths is let's say, no, not A, of course. It's B, and then we go through gate 1, and we go through gate 3, and then gate 5, and then F. Right? This is a path here. This is a critical path, okay? Another critical path is C135F. A third critical path is D235F, okay? And the fourth critical path is E235F, okay? All of them have the same longest delay, okay? Sometimes you have more than one critical path, and sometimes you have just one critical path. Any question? Okay, let's move on by discussing some exam questions, okay? Because we have time now, okay? I'm going to go back to the concepts by discussing some exam questions, at least for the remaining part of this lecture, and next time we will start another lecture, okay? So in this question here, another topic, I mean, we have f of a and b and c is equal to a complement b, or with a c complement, okay? We would like to express f as a sum of minterms using the sigma notation. This is an exam question. Okay, so if now is if in canonical form? This is a question to you. Is if is given in canonical form? The answer is no. Why? Because, for example, C is missing from this product here. Okay? Or you can say B is missing from this product. Okay? So for these two reasons, okay, or for one of them at least, F is not in canonical form, but it is in standard form, and it is in sum of product form, okay? So we need to convert every product to a minterm, okay? So we can use algebraic notation, algebraic manipulation for this. And the way to do this is to employ the AND identity plus the complement property. Now the A complement B can be equal to A complement B ANDed with 1, and this one can be replaced with C or C complement, okay? And then you use the distributive law to distribute this, okay? So this is equal to A, B, A complement B, C, or with A complement B, C complement. and this one is minterm number 3, and this one is minterm number 2. Okay. Now for the other one, which is A, C complement, you introduce the B now, which is the missing literal. Okay. So you end up with minterm number 6 and 4. Okay. So eventually your f of A and B and C is the sum of these minterms 2, 3, 4, and 6. Okay. And there is a shortcut here. You can employ this, but it does the same, actually the same exact job. Okay, so the shortcut is you have A complement B and then a dash here, missing dash here. Okay, so we have a 0, here and a 1 here, and then a dash here. Okay, so 0, 1 can be, the last one can be a 0 or a 1. Okay, so this corresponds to a 2 and this corresponds to a 3. Okay, then we have an A dash C complement, which corresponds to 1 at the most significant bit and a 0 at the least significant bit, and in between we have a 0 and 1. So for this case we have a 4, and for this case we have a 6. Okay, so the minterms that we have again are 2, 3, 4, and 6. Okay, any question? Okay, moving on.
Doctor.
Yeah.
What if we wanted to do the shortcut, but with the max instead of the min?
Yeah, I mean it's then you flip the. Okay, let's do that. First of all, if you want to do the max terms, then what does the question say? Okay, the question, for example, if it is let's say that you have A or B complement, okay, and you would like to use the shortcut here. So this is going to be corresponding to what? To a 0, right? And this is going to be corresponding to a 1, okay? The B complement is going to be corresponding to a 1, all right? And then you have a hyphen here, okay? So this is going to be either 0, 1, 0 or 0, 1, 1, okay? Which is, this is minterm number 2, max term, I'm sorry, and this is max term number 3. And to verify this, you can do algebraically A or B complement is ORed with actually C complement, okay, which is 0. And then you use distributive law, which is A or B complement, ORed with C, and with A or B complement, ORed with C complement, okay? So what is this? This is max term number 0. Hold on. Yeah. So yeah, 0, 1, 0. All right. And then this is max term number 0, 1, 1. Okay. Yeah. So
yes.
Yeah. Let me just double check that. Okay. Double check. If we complement, get in complement B C complement, and that is going to be 0, 1, 0. Yeah, excellent. Yes, this is the. So I just converted this to the. I just took the complement of this to see if we are doing the right thing. Okay, the complement of this is going to correspond to minterm number 2. So this the complement of this as well is going to correspond to max term number 2. Okay. So for uncomplemented variables, you get a 0 in max term, and for complemented variables, you get a 1. Okay, so this is the way to do it. Now, if you have 2 variables missing, then you have 2 dashes. Okay, so if you have 2 dashes, then you have 4 possibilities. Okay, this can be a 0, 0, 0, 1, 1, 0, 1, 1. Okay, and you list them and do the convert them to decimal and take the corresponding indices. Okay.
Okay, clear. Thank you.
Sure. Okay, we would like to express this in, this is given as G, okay, AB ordered with C complement D. This is expressed in sum of product. We would like to express G in product of sums standard form. Now we can use either the distributive law to do that. Okay, so because this, we can OR it with AB and then take D, OR it with AB, okay, like this. All right, and then take the C complement and OR it with A once, and then take the C complement and OR it with B once. So you get these four sums that are multiplied by each other. Okay, this is the first solution. The second solution is to take the dual of G. Okay, and to take the dual of G, okay, you can say, well, G is what? AB ORed with C complement D, right? Yeah. So if you want to take the dual of this, what is the dual of this? It's A or B, ANDed with C complement or D, right? Then use the distributive law again, okay? So no getting away from the distributive law. So it's going to be A or B into C complement, ORed with A or B into what? Into D, okay? And this is going to be equal to A C complement, ORed with B C complement, ORed with AD, ORed with BD, okay? And then you take the dual back to go back to the original function, okay? So if you take the dual back, you'll get the same expression as this one, maybe minus the order, okay? However, I think it's even the same order, yeah, luckily. Okay, you get that? Okay, so there are two ways of doing this. This is one way of doing it. Okay, I gave you two ways, and you may think of another way, of course. I don't know, okay? So the wrong thing to do here is to convert this to a product of max terms. Okay, do not do that. We are asking you to convert it to a sum, a product of sums that is not considered as a product of max terms. Okay. All right. We would like you to see how we would like to see how you manipulate the expressions in algebraically. Okay. All right, next questions. Okay, this is a big question from one of the exams. Okay, I'm not going to do part A and B. So let's quickly do this part here without doing this part. Okay, how can we do that? How can we do this? So we have G, okay, and we would like to express it in some of minterms notation using the sigma notation. How can we do that? We have to change every product into a minterm, right? So for the first one, we have 0, 1, and then dash. Okay, so this is what? This is 0, 1, 0, 1, and then dash. The Z is missing. So this is 2 and 3. And for the second one, we have X and Z. So we have a 1 dash 1. Okay, so this is either 101 or 111. So this is 5 or 7. Okay, and for the last one, we have dash 1 1. Okay. By the way, we don't have to do this. If you remember the consensus theorem, this term is redundant, so we don't have to do it. But let's do it. Okay. I mean, in canonical forms, you'll find that this is repeated. Okay. You'll find that it is going to show up in one of these two forms. Okay, in one of these two indices. Okay. So it can be 0, 1, 1, which is 3. Already there. It can be 1, 1, 1, which is 7, which is already there. Okay. So my function G of x, y, and z is nothing but sigma of minterms 2, 3, 5, and 7. Okay. Okay, what about the second one? First of all, I need to find the indices of max terms. What are the indices? Pi of, what are the indices? Who can tell me? I have probably an answer in the chat. 0, we have 0, 1, 4. Do you agree, guys? These are the missing indices indeed, okay? 0, 1, 4. So the 0 is going to be A or B. I mean, it's X or Y or Z, okay? And then 0, 1, 0, 0, 1. The 6 is missing here. Yeah, 6 is missing. Excellent. You have 6 as well. Okay. 0, 1, 4, and 6. Yeah. Whatever indices that are missing from here, because we have 8 max terms, and we are, yeah, we have 8 max terms. Minus 4 is 4. We should expect 4 as well. Okay. All right. So what is this going to be? 0, 0, 1 is X or Y or Z complement, and then what? 1, 0, 0, which is X complement or Y or Z, and finally 1, 1, 0, which is X complement or Y complement or Z. Easy, right? And this is what? This is G of X, Y, and Z. Okay. All right. Now this is a question on the operations of the canonical forms. So we would like to find, so in one of the forms you are given algebraic form, so you need to convert it to a product form, right? Product of M, which are what? 0, 0, 1. This is 1. This is 1, and this is what? 0, 1, 0. This is 2 and 3, and then 5, right? 1, 2, 3, and 5. Please tell me if I did something wrong, okay? Let's do this quickly and then call it a day, okay? So we have if ended with G in a sigma notation. So I need to change this to sigma. So what is this in sigma? It is going to be 0, 1, 2, 3, 4, 6, and 7, okay? So I need to complement that. So the complement is going to be the same as these indices here, okay? So I have this intersection with these, okay? So we have the 0 is not showing. So let me say F ended with G complement is going to be equal to sigma. The 0 is not showing, and the 1 is not showing. The 2 is showing. The 4 is not showing. The 3 is not showing in both, and the 5 is showing. Okay, so the answer is going to be 2 and 5. Do you see that? Any questions? So let me stop here. I'm sorry for taking one more minute of your time. Okay, so let me stop here. By the way, at the end there is an example of a delay. I'm not going to do that. Just do it yourself and make sure that you get it right. Okay. These notes are going to be uploaded today to the Blackboard. So find them and try to practice them as much as you can. Let me stop recording.